So today, last week, no, last Tuesday, I just summarized the whole semester for the circuit analysis, and well, it will not be in any quiz or exam, so 都不考了。Okay, so today I'll cover chapter 32, which is about Maxwell equation. The first part is about the first Maxwell equation, and the second part is the magnetism of matter. And actually, up to this part is the Maxwell equation, and the later part, you can regard it as some informative stuff. So it is something like hardcore physics. So actually, I don't know about it because it's difficult. Maxwell equation is easy because you can imagine it, but the later part is about the quantum mechanics, so it is very difficult. No ways to imagine. So you can just think you listen to a story and that's it. So first, so it's the Gauss law for magnetic field. So in chapter 23, we have learned the Gauss law for electricity, which is this one. So you are very familiar with it. The surface integral of the electric field over a closed surface equals to the enclosed charge over the permittivity. And actually, for Gauss law for magnetic fields, it is more or less the same on the left side, except we change the E field into magnetic field, and still it is a closed surface integral. And the right side, it is simpler, and it is actually zero, because as I mentioned before, there are no magnetic dipole. So you cannot say, oh, there is a net magnetic charge, something like that, in the closed surface. So you have no magnetic dipole. You only have magnetic. You only have magnetic dipole. You don't have any magnetic monopole. So which means that you cannot separate the magnetic into positive magnetic or negative magnetic. They will appear together. So on the right side there is zero. So it is easy if you have know what is Gauss law. So this figure shows that if you have a long magnetic bar and then you break it into three pieces, so you have small magnetic dipole, something like that. So you cannot have one segment to be north pole, one segment to be south pole. No. So far, in the experiment, we cannot create that magnetic monopole. Okay, so for the next one is the induced magnetic field. So for the left side, you have learned it in chapter 29. It is the Amperes law. So at that time, this line integral for magnetic field over a Amperes loop or a contour is mu0 I. I is the current enclosed by this loop. But here is mentioned that actually on the left side is the same line integral, but for the right side it is a little bit different. Still mu0, but we have this term epsilon 0 time derivative to the electric flux over this surface. So this is electric flux, the derivative or the rate of change of the electric flux over a surface. It is not a closed surface as Gauss law. This is closed surface. Here, this is not closed, only over a loop. So the derivative of it is proportional to this term. And actually, which means that if the electric flux over this surface is changing, then it will generate a magnetic field. This is implied by this so-called the Maxwell's law, the Maxwell's law. And okay, for Amperes law is something like a static current. It will generate a magnetic field rotating around the current. For this time is something like you have a capacitor here. So when you learn in high school, DC signal cannot go through this capacitor. So the charge goes to here and then it will settle. But as you know that in circuit analysis, you know that I equals d dV dt, which means that if the V, the voltage between these two plates is changing, there will be current. There is not a real current going from this side to this side, but as long as the charge accumulates on these two plates can vary. There is something like the AC signal can go through it. And as you know, last lecture I mentioned that the impedance for capacitor is 1 over j omega c. So you can imagine if omega is 0, which means this is a DC, then the impedance is infinite. So DC signal cannot go through a capacitor. But here, if omega is very large, which means that if omega is large, which means that z of c is small, or the absolute value is small, so that signal with high frequency can go through it. It's something like you have a very small resistance so that all the signal can go through. Well, it's more or less like this. Induced magnetic field drop around the loop. So you'll see if the electric field pointing inside is changing, there will be a induced magnetic field. So these two laws are similar. So for the Faraday's law you learn in chapter 30, you have a line integral for the electric field. It is generated by the changing magnetic field. Here, if you have a varying electric field, you will also generate magnetic field, which means that change of magnetic field can generate E field, and change of E field can generate B field, and change of B field can generate E field, and loop together forever. So they are similar, but they are different in two ways. So one of that is that mu and epsilon 0 appear for matching SI unit, so that well, it's just to make the point is that the dimension of the both sides are the same, so it's not so special. And the next point is that this is positive on the right hand side, and this is negative on the right hand side. So for this case, the changing E field will generate clockwise E field, But for this case, changing B field will generate a counterclockwise of E field. But here it assumes that the changing is increasing. Is increasing. Is increasing. If it is decreasing, then the induced E field or B field should be in another way. So up till now, is there any questions?
surface 上面的 E 或者 B 来算它的 current。
No. 算他们的 current 没有 current。Actually, for the Amperes law, it is not mentioned here yet, but for Amperes law, it means that this is Amperes law. Which means that a static current will generate a B field. For example, if you have a static current going this way, so there will be a magnetic field rotating around this current. If you have a static current, but if it is a E field changing or the electric flux changing, then it will also generate the B field rotating around this. Or you can imagine display this something like that. So you should imagine this circle is rotating by 90 degrees perpendicular to the surface. This red circle should be something like this. Then this is a capacitor. So if the voltage between these two plates is changing, so you should expect there will be a B field, the magnetic field, going this way or that way. Depends on whether the voltage is increasing or decreasing. Because a sine wave is something like that, so it will increase for half cycle and decrease for another half cycle. So there will be a magnetic field going this for half cycle, and then going backward for another half cycle, and then going back and forth.
可是它不是线性的，为什么说是对称的？因为它不是 ds 吗？不是 dA。
Oh. On the left side, this is a line integral, but this one is a surface integral. It's not closed surface, but it is a surface integral. In chapter 23, you have net flux and total flux. Total flux means the flux for a arbitrary surface, not necessarily to be closed, but for closed surface, it will enclose a volume, something like that. For the right side, it means that for the left side is a line integral. For example, if we make the contour or the Amperes loop like this, so that for the right side, the electric flux come on this surface, enclosed by this loop. Any other questions? Okay, just mentioned this already. No. Not yet. So we go on. So in chapter 29, we have learned the Amperes law, and here we mentioned the Maxwell's law. It is the representation of this textbook, but for the next lecture, I will show you another way that, oh, it seems like, okay, in the textbook, it's mentioned that, oh, Amperes law, Amperes find that, okay, uh, Amperes law should look like this. And Maxwell think, oh, it should look like this. So why not combine them together? Why not combine them together? Because, okay, I don't know how to, when to use this or when to use that. So why not combine them together? But for the next lecture, I'll tell you that you don't really need to add the third term, because up till now, if I just told you, oh, here, A find that it should be look like A, M find that it should look like M. Why not A plus M? But you may ask, oh, why not add the third term or fourth term? But next lecture, I'll explain to you why these two terms is the exact term we need. But according to the representation of the textbook, it is mentioned like this. So up till now, I follow it, and next week I'll show you why. So actually, it tells you that Amperes Maxwell law is just adding them together. So we have the line integral on the left side. So on the right side, we have mu I enclosed and also mu epsilon 0 d phi e dt. So this is called the Amperes Maxwell law. So nothing special. If you already know these two, so I just add them together. And why we can add them together? Because it is linear. Linear means you can separate them. You solve A and B and then you add them together. Because you have learned it in signal and system or any other theory. You know that linear system means if I have x to be the x1 to be the output, so that you have y1, so that if you have ax1 to be the input and you will have ay1 to be the output. If you have x2 to be the input and you will have y2 to be the output, and if you have ax1 plus bx1 to be the input, and then you will have ay1 by1 to be the output, then it is linear. It's a linear system. And actually, linear system is easy to interpret, not necessarily easy to calculate, because Maxwell equation can be quite difficult to solve. And in the next lecture, I'll show you how to, because you just asked a very interesting question. This is a line integral. This is a surface integral. How to link them together? And then next lecture, I'll show you how we can link them together. Because I believe you have learned it in calculus class. You may have learned the Stokes law and the divergence law, or the Gauss divergence theorem and Stokes theorem. So it will relate to this stuff. Because you know, at that time Stokes was managing an examination, and then it made the Stokes theorem as the problem. You think of this fancy theorem, and then you make it to be the problem. And Maxwell was one of the students to take this exam, and he's the only one who can solve it during the exam. So he actually used it to derive many famous result. So finally, it is called the Maxwell equation, because none of the law in the Maxwell equation feel like strongly related to him. And here it mentioned that there's a current, but no less electric flux. Then you only have this term, and this term will be 0. And so it will reduce to Ampere's law. If you only have the time varying E field without the current, then this one is not 0 and this one is 0, and it will reduce to Maxwell law. But actually, I think it is possible to have both. But here is mentioned that in Ampere Maxwell law include both of them. Sample problem. Okay, so this is the parallel plate capacitor I just shown in previous page with circular plate. So this is a circular plate of radius r is being charged. Derive an expression for the magnetic field at radius r for the case r smaller than capital R. So this is the cross section. This is the cross section for. So you imagine this is the cross section. You cut it here. You cut it here. So actually, if there are varying electric field, so you should consider the Maxwell's laws. So the Maxwell's law like this, and actually we know that the magnetic field is also like a circle, And as we know for parallel plate capacitor, the E field is uniform. So we can simply write E times A, but not the integral. So on the left side, it is 2 pi B times 2 pi R. And the right side, mu 0 epsilon 0. A is a constant, so we can fractate out and dE dt is left inside the derivative. And actually, A is pi r squared. So we substitute A into the right side, and finally we will get mu 0 epsilon 0 r over 2 times dE dt. So it should be quite easy. Okay, so next evaluate field magnitude B for blah 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 blah. So we just substitute all the value inside. Mu 0 epsilon 0 r over 2 dE dt. And mu 0 is 4 pi times 10 to minus 7. Epsilon 0 is 8.85 times 10 to minus 12. Small r is 11 millimeter over 2. And dE is 1.5, dE dt is 1.5 times 10 to 12. So it is 9.18 times 10 to minus 8 Tesla. So it is nothing special. So it also asks you to derive an expression for the magnetic field at the radius r larger than capital R. 没看到结果。Okay, next, so here, we still use the Maxwell's law, d phi e dt. And similarly, on the left side, it is b times 2 pi r. And on the right side, a dE dt. This time a is pi capital R squared, because we assume that the parallel plate is circular with radius capital R, so that we do not we will ignore the electric field outside the plate, but we consider the magnetic field outside. So so the surface integral only count this area. But for the line integral, you need to consider the small r. So finally, E will be equals to mu 0 epsilon 0 capital R squared over 2r dE dt. And this is this is E. This is E. So up till now, any questions? Now we move on. So here we also define a term called displacement current. So if you compare the two terms on the right side, Amperes law and Maxwell's law, Maxwell's law, you'll see that the product, this one have the same dimension of a current, because you have mu times I enclosed and mu0 times this one. So this one should have the same dimension with this one. And dimension tracking is very useful whenever you need to derive some equation, because it is an easy check that you may make some error, especially sometimes you integrate and then you don't care about something like per volume, per surface, per line, the length, and then you may make the dimension not match. Then you'll see, oh, okay, let's try to find where's the mistakes. And actually here, of course, the Ampere Maxwell's law is correct, and then it tells you that the current should have the same dimension of this term, and this term is divided, or it is called displacement current, 位移电流 ID. So we have the displacement current. Actually, it is something like the current going through the capacitor, but you know, DC current cannot go through a capacitor, but only the AC current can go in through the capacitor. You can imagine something like this. We have this term is the displacement current, and we can rewrite it something like this. So for parallel plate capacitor, so we assume that the E field is uniform. So we can write it like this, because phi E is E times A, and then A is constant, so that we can move it to the front. And maybe you can feel something similar, and then we try to divide it by D and multiply it by D here. So it will be something interesting. You can know that this one is the parallel plate capacitor, so that you could have C here. And when the E field is uniform, E times D is the voltage, or the electric potential. So it will look like this. And then this is the current for the capacitor. So that you can imagine the displacement current like this. This is actually the current of the capacitor. When I learned that, the professor said that, oh, it is a displacement current. It is not a real current, but what is not real is fake or whatever. But actually, you can understand it like this. It is actually the current of a capacitor, and then you can write it like this, but it is not so important because it only makes the equation more compact. But if you only see that, you lost some information. It only makes it better looking, in my opinion. So we try to explain what is a displacement current. Finding the induced magnetic field. So as I mentioned, this is something like the parallel plate capacitor. The parallel plate is circular, and as long as you have some current, and it will generate a B field, something like that. If this current is increasing, constantly increasing, then the B field will be a constant because it is the derivative of the electric flux. But if it is not constantly increasing, then it's not easy to describe. Or if it is a sine wave, then it is another sine wave with 90-degree phase shift. Because you take derivative to sine, it will become cosine, take derivative to cosine, and then it will become a minus sine. So 90-degree phase shift all the way. And this is similar to what we derive, similar to what we have derived in the yeah, something like that. Yeah, but this is not really important, I think. So there is another example. The circular parallel plate capacitor is being charged with a current I. So between the plate, what is the magnitude of this line integral in terms of mu0 I at the radius r equals to capital R over 5? Okay, so we will have B ds equals to mu 0 I d enclosed the displacement current, and I, and I is the total current, and the enclosed displacement current is follows this equation, something like this: ID equals pi r square over pi capital R square. Because the current is uniform, sorry, I mean the electric field should be uniform, and the current actually is also uniform. The displacement current is uniform also, so it's proportional to the area. So for the total displacement current, it is pi r square for the whole capacitor, and the enclosed one is the smaller one, so it is proportional to pi r square. So when they divide each other, so it is something like 1/25. 1/25. Ouch. One over 25. So and actually this is I. ID is actually I. So finally, we will have B ds, which is actually mu0 I 25, because I mentioned ID is actually I, so we multiply I on both sides, so ID enclosed is I over 25. So for B, in terms of maximum induced magnetic field, what is the magnitude of the magnetic field induced at inside the capacitor? Okay, so we have B of R equals mu 0 I 2 pi R squared R times R. Which means it is actually proportional to R because this is constant. So which means that the maximum is that BR maximum will be B capital R, and R is 1/5 of capital R, so it will be 1/5, and you can write it as BR equals B max over 5. B max over 5. Any questions? So the Maxwell equation in this textbook is described like this, and actually I don't think it is enough. So in the next lecture, I will give some supplementary notes about the Maxwell equation. I will show you something about the differential form for the Maxwell equation and also the conservation of charge, because it is very important to derive the wave equation so that in chapter 23 you learn the electromagnetic wave. And in the textbook, I don't think it is written very well, so that you will not know how does it come from. And you have many question marks in your head, and it will be very hard to explain right without introducing the differential form of the Maxwell equation. So that for the next lecture, there will be a little bit more math. Actually, all of them are math, but this is the only way you will be able to know why it looks like this. And for chapter 33, it is actually the solution for the wave equation, which is actually a PDE without boundary condition, so that it will not be too difficult. As you know, if you have learned how to solve a PDE, if it has a boundary value, boundary condition, it will be very complicated to solve. But if I have time at the end of this semester, I will teach something about the quantum mechanics. Then it will have something like the PDE with boundary condition. Then you know something about the quantum phenomena, which is really interesting, because without telling you, you can never imagine the world look like this. And so the Maxwell equation is present like this, and I think this chapter is very weak in my opinion. when I study physics 2 in my bachelor study, actually I also use this textbook, but at that time the professor said that, oh, this textbook is garbage, so I don't use that. And she wrote her own lecture notes, and we follow that to have lecture. And up till now, I think the previous half is improved quite a lot, because at that time it is version 4 edition, 4th edition, and now it is something like 10th edition, if I remember correctly. And for the previous part, it is described quite good, but up till now, it is not really good, in my opinion. So I have some supplementary to you. So I think for the math part for chapter 32 is more or less conclude, and the remaining part is something like a story, so you can relax, and I'll try to go through it quickly, and then I will go to the sports day. Actually, so here, well, it's actually difficult. It is something hardcore physics, so that I'm not a physics guy, so I don't know much about it, but I try to explain it to you. So actually, up till now, you know that we don't have magnetic dipole, magnetic monopole. We only have magnetic dipole, but we still want to know how the magnetic field comes from. We know that it can be generated by the current. It can be generated by magnetic bar. It can be generated by time varying magnetic electric field. But can we find the unit element to generate the magnetic field? This is what the physicists want to do. And at this page, it shows that actually the Earth is a big magnetic. It's a huge magnetic, as you know. You know the compass, so that you can know the direction. But actually, for the Earth, you know that the south pole of the magnetic is not exactly the same as the geometric north pole. Yeah, there are some difference between them. So if you are very close to the north pole or south pole, then the compass didn't work. Actually, why do the Earth have magnetic field? Thing is that the Earth is rotating. You know, as you know, so that we'll have day and night because of the Earth is rotating at every second, and yeah, it's something like that. And actually, the magnetic field for the Earth is a very good shield for the Earth. If there is no magnetic field in the Earth, we'll all die, because there are many high energy particles, something like the X-ray, which will shooting the Earth. And as you know, if we were inject too much by the high energy particle, something like the ultraviolet, the 紫外线, ultraviolet wave, and will be have more chance to have cancer, something like that. And actually, the magnetic field for the Earth try to shield the Earth, because you can imagine there's a magnetic field. So if you consider a charged particle is going in this way. This is the V going into the page, shooting the Earth, and magnetic field and the side are this way, but for this part it is something like this, So the magnetic field is pointing upward, and the Lorentz force is something like V cos V, so that the charged particle will be redirected by the magnetic field and was reflected by the magnetic field. But this is the weak point for the Earth. So if the high energy particle is shooting in this angle, then this shield cannot block the high energy particle. Then it will directly inject to the Earth, and then you will see the aurora, the 极光 is actually that. So don't you can try to look at it once or twice, but if you frequently there, then you may have more chance to have cancer. So and actually you see that in Northern European, Canada, or Chile, or South America, something like that, you'll see the aurora. And actually it's due to the magnetic field of the Earth. And this is even more difficult. It is related to the quantum mechanics. And so so far I cannot explain you why, but just a phenomenon. So we try to know how the magnetic field comes from. So actually, it tells you that an electron is always spinning. So if the electron is spinning, it will generate a magnetic moment, a magnetic dipole moment. And this is a philosophical problem, because you don't really know, you can't really observe an electron is rotating. If I have it is rotating, you can see it. If the Earth is rotating, you can still observe it, because if you have a camera on the space and then you look at the Earth, then you can know that Earth is rotating. But for an electron, you have no way to observe it is rotating. But how do we know the electron is rotating? Because it will generate the magnetic dipole moment, so that we will know that it spins, so that it generates the dipole moment without any other ways, so that we know that the electron is spinning. Then, due to this spinning, it will have something like the spin magnetic dipole moment. And actually, if the dipole moment is something like that, it should be derived from the Schrödinger equations, and then it is quantized. You may learn a bit about it in high school in the chemistry class, but there's no way to explain you why at that time, because it needs to solve the Schrödinger equation, which is a PDE. So it is not possible to explain it to you, so that you know, oh, there will be some quantum number, orbital angular momentum, orbital quantum number, something like that, and something like that, angular momentum, something like that. And as you know, the spin of the electron is something like 1/2 and -1/2. because it is due to the boundary condition of the PD, so that it cannot occur continuously. And the magnetic dipole moment due to the spin of the magnetic dipole is something like this is E, which is 1.6 times 10 to minus 19 coulomb, and the mass of an electron is 9.11 times 10 to minus 31 kilogram. You can check it on the table, and S is something like this, MS is 1/2 plus or minus 1/2, which is what you learn in chemistry in high school. And H is the Planck constant, 6.63 times 10 to minus 34, which is a very famous constant. When you learn the modern physics, you know E equals HF, something like that. And when I teach the quantum mechanics, maybe a few weeks later, then you know something very interesting. It is actually a constant inside the Schrödinger equation. And h over 2 pi, we will write it as h bar. H bar equals h over 2 pi. It is not mentioned in these textbooks, but if you define this called reduced Planck's constant, reduced Planck constant, then the Schrödinger equation will be have less term, will be better looking. So in quantum mechanics, they usually use the h bar rather than h. Sometimes they make the equation better looking. Well, yeah. It's something like the omega. Omega is 2 pi f. So f is the frequency, and this is the angular frequency. So that something multiplied by 2 pi, something divided by 2 pi, and then they will cancel. And then we substitute this dipole moment. What is that? Okay, we substitute this into here. Because spin is not observable. We can only measure the spin over one axis, for example, over z-axis, or over x-axis, or over y-axis. And if we measure the spin over a certain axis, it will be quantized. And we substitute it into here. Then we will have this term, just put it inside, and then this is so-called the Bohr magneton, which is you can imagine it is something like the unit magnetic. So it's something like this, and the energy regarding to this Bohr magneton is something like this. If you have an external B field outside, then when you have many magnetic dipoles, they will try to align to the external B field. But this is very difficult to imagine. So just regarding the story. Well, So other than the spinning, something like the Earth, it is rotating around the nucleus. The electrons should rotating around the nucleus. Something like the Earth is spinning, but it's also rotating around the sun. So for the electron, it's something like that. And then if it is rotating around an axis, it will also generate another dipole moment called the mu orbital, which is the magnetic dipole moment due to the orbital. And this is similar to that and this one is another quantum number. So it will come from a 0 plus or minus 1 plus or minus 2, something like that. And actually, you need to derive the Schrödinger equation with the hydrogen atom potential energy in the spherical coordination. Then you can find all the quantum number. So it will be very, very difficult. And yeah, it was something like that. And you also have the magnetic moment, magnetic dipole moment due to the orbital and something like this. So there are 3 types of magnetic. The first type is called the diamagnetism. Diamagnetism. In Chinese, it's called 抗磁性, which is something like a diamagnetic material placed in an external magnetic field, develop a magnetic field dipole moment direct opposite is the keyword to the external B field. So what will it happen? Okay, so here is a frog. This is a frog which is diamagnetic. And then this one is a solenoid. And then this should be the solenoid is placing strictly, and then you lock it from the top. And as you know, you can generate a B field by this one, and then so this will be the B field generated by the solenoid, and this frog is diamagnetic, so that it will generate a B field opposite to the external B field, which means that this 2 B field will make it declare with each other. So that in this case, you will observe that the frog is floating mid-air, and the frog moves upward into weaker and weaker magnetic field until upward magnetic force balance the gravitational force. Then it will something like floating, and the frog is not in discomfort because every atom is subject to the same forces, which means that there are no force dragging the frog, so it's not painful, and it is floating. So this is the diamagnetism. So the second type is called the paramagnetism, 顺磁性. The paramagnetic material placed in the external magnetic field. So it is opposite to the previous case. For paramagnetism, if you apply a external B field, then it will generate another B field which is at the same direction or attract towards the external B field. And here it shows another law called the this law. I don't know what it is, but actually it's called the Curie's law. You may have heard about her name. Her full name is Mary Curie, 居里夫人. So she's the one who invented the X-ray. So her law is show that when you apply the external magnetic field, divide by the absolute temperature in Kelvin. So it should be linear. To the M. M is something like this. And complete align saturation of all the dipole in the volume give a maximum value. So it assumes it is a linear relationship between the M and the external B field over the absolute temperature. But actually, during the experiment, we cannot observe the same phenomenon. Actually, in the experiment, it doesn't really match the Curie's law if the external B field is large enough, then it will try to saturate. And this is related to quantum theory as mentioned in this textbook, but I don't know what it really is. It is something called the measured magnetic moment over the volume. Because for the definition, it's mentioned that if you apply a external B field to the paramagnetic material, it will generate another magnetic field which have the same direction as the external field, so that the two magnetic field will add together, and then you generate a magnetic moment. And M is try to count the magnetic moment for a unit volume. But actually, this phenomenon will saturate, and due to the quantum theory. So it's something like that. And so here we still have another sample problem. So our paramagnetic gas at room temperature T equals 300 K is placed in an external uniform magnetic field of magnitude B equals 1.5 T, and the atom of the gas has magnetic dipole moment, which is 1 megaton, Bohr megaton. Calculate the mean translational kinetic energy of an atom of a gas and the energy difference delta UB. And in the so-called thermodynamics, you know that K equals 3/2 kT, and K is the Boltzmann constant times 1.38 times 10 to minus 23. equals to 6.2 times 10 to minus 28 joule. And for the delta UB, we know that it is something like mu B cosine 180 degree minus negative mu B cosine 0 degree, which means you need to rotate the magnetic dipole moment in the other way. So it will be equals to 2 mu B, because cosine 180 is minus 1, cosine 0 is 1, and you substitute 2 times 9.27 times 10 to minus 24 times 1.5. Well, so we have it just for fun. Actually, I don't know what it is, so I'm not asked it in the quiz or exam. I think I don't know what it is. Well, the final type of the magnetism is something like the ferromagnetism, which is what you usually see in your life. Ferromagnetism. So a ferromagnetism is something like if you place the ferromagnetic material in the external magnetic field, it will generate a magnetic dipole moment. But if you remove the external B field, the magnetic dipole moment generated by the ferromagnetic material will still be there. Okay, it should be something like this. This is called the hysteresis, 磁激效应, which means that originally, if the material don't generate any magnetic field, if you apply a external magnetic field, and if it is increases, then it will also generate a B field by that. And after you have remove all the magnetic field, all the external magnetic field, it will still have some magnetic dipole moment there. You need to apply a negative enough B field so that you can reset the magnetic dipole moment of the ferromagnetic material. And if you apply further negative dipole moment, it will look like this. If you go for a loop, it will go in this way. It will go this way. Dynamically, it is something like it don't have any magnetic dipole moment, and then you apply a plus magnetic field, then it will increase to this point, and then the external magnetic field is decreasing, so that the magnetic field generated by the ferromagnetic material will also decreasing, but slower than that. It's not really slower. It's something like it has some memory. And then it will move like this. The external B field is decreased to a negative value until here. Then you can reset the material, and you will go like this, go to there, something like that. So in the past, we used it as the floppy disk properties. It is something like the old school stuff. And when I was primary school, I still using that, something like the 3.5 inch properties, which can store 1 megabyte, 1.44 megabyte. And for when I was in kindergarten, something like that, still they're using the 5.25 inch, something like that, floppy, which can only store the hundreds of kilobytes. So when you need to play a game, you need to have a bunch of properties, so that okay, you insert this A and then it wait for 30 seconds, and then change to this B and change to this B and load for another 30 seconds, something like that, and then insert this C and then you start the game, something like that. And so they use it to record the data, because if you can control a magnetic disk, and then you give it some external B field, you can store the information here. For example, you can store 1 and 0, something like that. Then you can write some data on the magnetic material. So it tells you that the ferromagnetic material can be aligned by an external magnetic field, and after the external field is removed, remain partially aligned in region known as magnetic domain. So it will still have some magnetic moment. Then if you read this magnetic dipole, you know whether it is 1 or 0. But if you put a magnetic dipole near your floppy disk, then your information will be ruined by that.